I think I can say this is the most important topic. Why? Because number one, because you are a mechanical student. Number two, because this is a knowledge, a core knowledge when we talk about metals. You are and there's a lot of engineering application focusing on steel, okay, rather than other materials. As you can see from the background of this slide, the bridges, majority of the structure are made from steel. Okay, the car, the vehicle, the ship, a very large ship, a very thick metal plate, those are made of steel. Okay, which is iron. When we talk about steel, it contains iron and carbon. It is actually alloy system between the iron and the carbon, and it's involved phase diagram. Okay, remember phase diagram, we are missing between two elements. Okay, so the outcome from this lesson, you should be able to identify the major phases on the iron carbon diagram and explain their chief characteristic. How does it look like? Explain and use the term of hypoeutectoid, hypereutectoid, proeutectoid, and perlite. Then you should be able to identify the proeutectoid phases for a given alloys and compute its mass fraction together with mass fraction of perlite. Okay, there are so many new terms, perlite, eutectoid, and many more. Okay, this is seems like new for some of you, but for those who already take this course, I think you should familiar with these new terms. Okay, the characteristic of pure iron. Okay, it is good electrical and thermal conductivity. Pure iron, okay, very easily magnetized. But pure iron is soft and readily oxidized, okay, forming rust. Okay, this is the major drawback of using pure iron. However, by adding on just carbon, light element, okay, abundant element, it can produce a lot of benefits to our nation, okay, to our world, okay, which is born steel. Okay, how much? It's only less than 2% of carbon, small amount. Okay, the electron of iron, okay, at atmospheric pressure, okay, there are 3 electrons. One is alpha, gamma, and delta. Okay, they appear at variance at different temperature. Okay, room temperature, whatever you see iron in any application, it is in the BCC structure. We call it ferrite or alpha iron. A temperature for pure, I'm talking about pure iron. Okay, so at this temperature, 900 Celsius, then you can get austenite. And above that temperature, you get delta. Okay, it is BCC. So different electrodes, they have a different structure at different temperature, of course. Okay, so due to the electrodes, phase transformation does not only take place during solidification. What is solidification? A process transformation from liquid to solid. Okay, so liquid to solid is change the phase. Okay, liquid to solid. It's obvious. Phase liquid, phase solid. But after become a solid, which is first solid form is this one, delta. Okay, upon releasing the temperature or heat, it change the phase. Okay, until reach room temperature. So when we talk about solidification of pure metal, okay, solidification of pure metal happened at 1538. Okay, at this temperature. Above this temperature, there are liquid. Okay, and it's happened at isothermal reaction. How? Okay, if we draw the cooling curve, which is temperature versus time. Okay, for these changes from liquid to delta solid ion is like this. Okay, this is melting temperature, which is 1538. This is melting temperature. Okay, so upon cooling, it will freeze. This is freezing temperature also. It will solidify. And you may see there are transition occur at a constant temperature, which is liquid plus delta. Okay, after complete transformation, it will form a single delta. Single solid delta until it reach 1339. Okay, 1339. 1300 439 pula. 94. Okay, 94. Okay, and it will transform into another solid which is okay, solid transformation. Okay, liquid up until here, and then this reduction of temperature, you may see that it's transformed from delta to gamma to alpha until it reach room temperature. Okay, so for pure ions, this is how it looks like. You can see the grain boundary. There are one color, which is a white color, light color like this. There's only one single phase. What is it? It is pure ion. Okay, however, pure ion has little use. It is made much more useful by alloying it with other materials. Okay, adding a small amount of carbon to iron greatly strengthens it. Okay, if you look at this phase diagram of iron carbon, where the maximum carbon can be added is 6.77% of carbon in weight. Okay, even though it is 6.77, but carbon is very light element. So 6.77% is too much for carbon to occupy any interstice inside the iron crystal structure. Okay, this one is not liquid. It's just delta. I think this photo is coming from I think if you Google this iron carbon phase diagram, in fact, from Wikipedia, they mistakenly labeled this region. Supposed to it is only delta, but some phase diagram they show liquid plus delta. Actually, the correct one is only delta. Right. So that's the reason I always encourage you to go for a correct references. Do not rely too much on Wikipedia, because Wikipedia sources coming from anyone that register with Wikipedia. Not necessarily the information is correct. Okay, always go to a scientific journal. All right. So 2%, 2% of carbon. This give you a steel. Okay, not so much, only 2%. But look at the steel. There are so many applications. You can see on the bridge, inside the building, on the car body, on the ship, cables. There's so many of it. Okay, but the carbon content is only 2, and they are varied in terms of the performance. Some of them are soft, some of them are very hard. Okay, the variety of the carbon content between 0 to 2% influence the mechanical properties, will give a different mechanical properties of your steel, even though the content maximum is only at 2%. Okay, up until 2% of carbon, okay, still behave during solidification like a solid solution with carbon atom where the carbon is completely soluble in the Fe crystal structure. Okay, for example, if we look at this 0.5% carbon, okay, 0.5% carbon, okay, the behavior during the solidification, okay, above this temperature, it is liquid, and then it's forming liquid plus something element, okay, and then below this temperature, it's forming the, let me see, 0.5. Where is 0.5? It is about this region. Okay, this region, it is about 0.5. So if you draw a line, okay, draw a line, you may see that metals start to solidify at temperature around 1400 something, and lowering the temperature, you will obtain two phases, which is liquid plus austenite. Liquid coming from the right side, austenite coming from the left side. Okay, and then below this temperature, it will become solid single phase austenite. Gamma, its name is austenite. And then entering this region where it has two phases. From the right side is austenite, from the left side is alpha. Okay. So now it is liquid from here, and then here is a liquid plus austenite, and here is austenite. Okay, gamma. Gamma has, the gamma symbol of iron has name, which is austenite. Okay, what is austenite? It's a FCC lattice structure of gamma iron with carbon atom within the interstitial space. Okay, this is austenite. And then due to allotropy, when temperature drops, iron eventually changes its FCC structure and transform into BCC, ferrite alpha. Okay, ferrite iron or alpha iron. Okay, this transformation happened in already solidified microstructure. So the transformation in the solid condition. Okay, so this one is liquid. This one is liquid plus gamma. This one is gamma. This one is gamma plus alpha. And at room temperature it is alpha. Okay. So it changed its microstructure from FCC to BCC, and due to the allotrope, it changed the microstructure. If it has a FCC, it's forming. If there is a carbon between iron in the austenite, it's forming FCC. Okay, and due to the allotrope, it changed to no, because of SCC, there are carbon at the center. But when it changed to BCC, the carbon will shift to the outside BCC because it's already dense with the body-centered structure. So the carbon forming cementite. Okay, react with combine with other iron atoms and forming another structure called cementite. Okay, so what happened is, this is gamma at within this range, and then this is alpha, and at this region it is alpha plus cementite. Okay, so alpha plus cementite. So this BCC structure, we call it ferrite. Alpha, we call it ferrite. Okay. right. Let me correct this figure first. Okay, so it should not suppose like this. Okay, this is 0.5. Okay. The correction is here. All right, and then lower to this. This one is wrong. Okay, why is at 7 to 7 you can see a constant temperature due to the isothermal reaction. Right? At this point, the carbon inside FCC structure, which is from austenite, at this point, this carbon forming cementite. Okay, so this is what happened. Okay, for the where's the 0.5? Okay, let's say this is your alloy. Just now we talked about 0.5% carbon. Okay, yeah, from austenite, and then austenite forming ferrite. The carbon is removed from this austenite crystal structure and forming this what we call it ferrite. And then at this point, this isothermal reaction, okay, the horizontal line in the phase diagram basically associate with isothermal reaction. So what is the reaction name here? This reaction name. Remember, to identify isothermal reaction, we have this kind of structure or this kind of structure. Okay, it can be solid 1 plus solid 2, and solid 2 plus solid 3. Okay, or for this is eutectone. So for this case, this is gamma, and below we have alpha plus cementite for the case general iron carbon phase diagram. So now it's reduced to this temperature and entering this region where the new phase form, which is ferrite, and then after it's reached this horizontal line, there is a constant temperature that allow austenite transform into pearlite or ferrite combined cementite. Okay, if you look at the original phase diagram, okay, okay, original phase diagram, we have the most end, the terminal elements here is alpha, and the terminal on the right side is cementite. Okay, if you zoom in here, it is cementite, Fe3C. Okay, so the oh, sorry. Okay, this terminal at the cementite or iron carbide, okay, is at room temperature is combined from left to right. So at the bottom is forming Fe3C alpha plus Fe3C, which is iron carbide. All right. So this one I will further refine. Don't worry. Okay. Okay. So this isothermal reaction here at 0.77% carbon. Okay, we have austenite phase. Okay, tak apalah. Alright, so if we have this kind of isothermal reaction like this, so we have austenite, and upon temperature reduction, it's forming two phases, which is alpha plus cementite. Okay, so exactly at this point, which is 0.77% carbon, exactly at this point, remember what's microstructure? It is a lamellar structure. Okay, 100% lamellar structure. Okay, this lamellar structure at exactly at 0.77 carbon, we call it perlite. So that's the reason you got perlite here. This is perlite. Okay, so this perlite, these are hyper-eutated region, you got perlite plus cementite, because cementite coming from the right side. And at this region, you got perlite with ferrite, because ferrite coming from this side. Okay, right. The carbon content in the iron, gamma iron, is the pressed out of the lattice structure during transformation from gamma to alpha, okay, ataupun ferrite. So the solubility of carbon in austenite decrease with decreasing temperature. Okay, so meaning that in the microstructure of FCC, iron, remember iron at certain temperature is forming FCC. So inside there is a carbon, okay, it's forming austenite. But if SCC change to BCC, this one need to be pressed out, okay. FCC interstitial is 0.4 times the diameter of iron, but carbon is 0.6 times the diameter of its diameter is 0.6 times. Okay. So as the temperature drop, lattice deterioration become too strong, and that's the reason this will cause carbon atoms being pressed out of austenite. Okay. Carbon atoms come together to form hexagonal lattice, which is graphite. Okay, hexagon shape. Okay, this is carbon graphite. Okay, normal graphite bonding, atomic bonding. Basically, this one is on graphite is can be observed in the cast iron. What is cast iron? Cast iron is a carbon content larger than 2%. Okay, so when the concentration of carbon is larger than 2%, then you can see graphite. This guy. All right. However, when FCC change to ferrite, where is carbon go? Carbon go outside and forming bonding with another 3 iron. Okay, like this. So this is 3 iron and 1 carbon. So we call it cementite. Okay, cementite, which is exactly Fe. Portion of Fe is 3 and 1 atoms of carbon. So then, meaning that when changes to this BCC, the carbon will concentrated and forming the cementite. Okay, and this is happen if you are having steel, which is carbon is less than 2%. All right. So the steel, there are several types of steel. Okay. When we talk about steel, we always refer, when we differentiate the types of steel, we refer to the microstructure, and it relates to the carbon composition. There are eutated steel, hypo-eutated steel, and hyper-eutated steel. Okay, eutated steel is a steel that's located at the eutated point. Okay, what is the composition of the eutated steel? It is 0.77. Where is it? Exactly this amount. Okay, it is 0.77% carbon in the iron. Okay, when upon cooling, okay, from liquid, and then you get austenite in the solid form, and then reach this temperature. What temperature? 7 to 7 degrees Celsius. Okay, it will stop here until austenite completely transformed into 2 phases. Okay, perlite. What is composition of perlite? It is a lamellar structure that consists of ferrite alpha, not ferrite alpha, ferrite iron or alpha iron plus cementite. Okay, or the name is ferrite plus cementite. Okay, so this is irritated steel. The composition is like this, the microstructure. You can see a grain boundary here, right? The grain boundary. And inside the grain, there are only lamellar structure. This lamellar structure, we call it pearlite. Okay. If I may zoom in, okay, you can see the microstructure. It is a pearlite. This is irritated steel if we observe under microscope. Okay, it's a lamellar structure, a very fine lamellar structure. This changes orientation. This is very fine lamellar structure. Okay, this steel is having irritated composition. Once the temperature is lower below the irritated temperature, the steel becomes both ferrite and cementite in the lamellar structure, and we call it pearlite. Okay, so remember from the phase diagram where the composition is 0.77, where the above composition is gamma or austenite, and below this temperature you get alpha plus cementite. Okay, there are two phases. One is solid alpha, one is cementite. So the reaction is gamma produce alpha plus cementite. At temperature composition 0.77%, and the temperature is 7 to 7 degrees Celsius. So only one temperature. So the cooling curve for this irritated alloy is like this: 7 to 7 temperature versus time. Okay, so the cooling curve is similar to the pure metal. And this is the microstructure. All right, hypo. We talk about hypo of what? Irritated. So this is irritated point. Hypo is at this side. Okay, the left side. Okay, the composition of hypo-irritated steel lie on the left side of irritated composition. Where is irritated composition? It is 0.77 percentage of carbon. Okay, so similar to the previous chapter when we talk about bismuth copper alloy, plumbum stannum alloy, okay, binary system with limited solid solubility in chapter 6. Okay, similar to that. However, for previous example, we talk about eutectic alloy. For eutectic also, it has microstructure that having lamella, isn't it? Lamella. And if composition located at the left region, we call it hypo-eutectic alloy of that particular system. So similar to that, but this case we talk about eutectic isotopic reaction, where in eutectic is involved reaction from one solid to solid. Okay, one solid, carbon. Okay, one solid is alpha, another solid is cementite. Okay, so hypo is on the left side. So the solid, the phase transformation happen like this. Okay, first is a gamma or austenite, only one single phase. You can see grain structure like this. This is grain, this is grain boundary. This is grain boundary. Okay, one single phase, which is gamma. This is gamma, gamma, gamma. They are all gamma. Okay. However, when it's entering this region, okay, at this point, what happened is new phase is forming. What phase? It is a alpha. Okay, austenite come from this right side. This is alpha. Okay, the small region here, maximum 0.02. Okay, this small region here, located here, this region, it is alpha. Okay, maximum composition is only 0.022% carbon. So alpha coming from the left, so that's the reason you get a mixture between alpha and gamma. So new phase is formed, which is alpha. The name of alpha is ferrite. But if it is hypoeutated alloy, okay, we call it the first phase because we know that at the bottom there are alpha and cementite also. Okay, this alpha need to be differentiated between this alpha, okay, the alpha that forms transform from the arsenide. Okay, so this first formation of alpha, we call it pro-eutated ferrite. Okay, in chapter 6, the first phase, solid phase, before entering into the region where they got lamellar structure, that phase we call primary alpha, primary beta. But in the case of eutated alloy, which is steel, we call it pro-eutated ferrite. Okay, pro-eutated. Where is pro-eutated? If you have this composition of steel, for example, 1.7 carbon steel. So this first phase formation, we call it pro-eutated. If you have this composition, okay, the first formation of new phase, which is cementite. Okay, arsenide is already formed here at this region. New phase is a cementite. For this case, okay, for this case, which is, for example, 0.3% of steel, of carbon. So for this case, okay, whatever new phase form at this point is called pro-eutated. Okay, pro-eutated. So pro-eutated will form at the grain boundary. Why? Because it is a weakest point. Weakest point where diffusion easily occur at the grain boundary. They will first forming at the grain boundary and continuously forming new nucleus formation of alpha at the grain boundary. And then when it passing through this point, it will form, okay, what is the phases here? Here is a perlite. Okay, perlite. So alpha coming from the left, perlite coming from the right. So alpha plus perlite. So alpha is there coming from the pro-eutated ferrite. So new phase formed at this temperature, which is 7 to 7 degrees Celsius, is a perlite. So perlite will start to continue grow at the active region, which is the point where the formation of ferrite occur. So it will grow from this point and grow larger until all the austenite transform into perlite. Okay, only austenite will transform into perlite. Whatever you have earlier, which is pro-eutated ferrite, it will remain as a ferrite, and only austenite will transform into perlite. So this guy will be perlite. The orange region will turn into perlite. Okay, so the initial formation at the grain boundary is pro-eutated ferrite. So that's the reason you will obtain. That's the reason for pro-eutated hypoeutated steel. You can see that the ferrite, the white, the yellow region forming at the grain boundary. Okay, this is the initial point transformation from austenite. Okay, the grain boundary already occupied with pro-eutated ferrite. Okay, so okay, this is the first transformation from austenite, and then the remaining austenite will form perlite. Okay, so this statement, remaining austenite will have eutated composition. What is eutated composition? It is a discomposition, perlite. Okay, perlite. And the perlite structure is a lamellar structure. It's occur at isothermal reaction because it's passing through this temperature, 7 to 7 degrees Celsius. Okay, so we call it hypoeutated steel. So if we observe under microscope, okay, okay, this is a scanning electron microscope. scanning electron microscope, or SEM image. This SEM image is giving a three-dimensional image surface. Okay, so the three-dimensional, that's the reason you see the protein from the surface. This protein that appear to protrude from the surface, this structure is cementite. Cementite. So the remaining structure is like an embossed structure, is alpha. Okay, so if you look at this structure, this is cementite. Okay, cementite, a layer of cementite with the this cementite that protrude from the surface is a hard surface. Okay, they are hard, and why it is protrude? Because during the sample preparation, it's they have a different behavior during grinding process, or whatever the process you conducted during preparing the sample. So they one is soft, one is hard. So that's the reason they appear differently in the microstructure. Okay, in the under the scanning electron microstructure. So another type is hyper. Remember, for hyper, it is located at the right side. Okay, similar to the hypoetheted. Hypoetheted, okay, is initially it is austenite. At this point, it's forming new phase. What is it? Cementite. And the cementite will first form at the grain boundary, and the name of this first cementite is pro-eutected cementite. And it will grow along the grain boundary until it reach the isothermal reaction, which is eutected temperature. Okay, when you reach this point, okay, at a constant temperature, whatever austenite, this is austenite. Whatever austenite, which is in orange light structure, remain in the structure, will transform into pearlite. Okay, so we have two different phases here. One is pro-eutected cementite, and one is pearlite. Okay, sorry, this is hyper. For hyper, all right, since the cementite, pro-eutected cementite form at the grain boundary, so the grain itself is the pearlite. Okay, the grain itself is a pearlite. The grain boundary is dominated by cementite, and this cementite is pro-eutected cementite. Okay, so there are another cementite in the in the pearlite. Okay, in the pearlite. So inside the pearlite, there are ferrite plus cementite. Okay, so there are two different locations of cementite. One at the grain boundary, where we call it pro-eutected cementite. Another one inside the pearlite. Okay. So again, remaining gamma or austenite, we have eutected composition. Okay, and it will transfer into pearlite isothermally. All right, again, remember, for the hyper, the grain boundary is dominated by cementite. So that's the reason grain boundary here, you can see protrude structure. Okay, protrude from the surface. This is because it is a cementite. This guy is cementite, and it is hard. Okay, you can see the pro-eutected cementite residing at the grain boundary, surrounding by pearlite eutectoid. Okay, inside the pearlite also, you can see there are some cementite. Okay, so now the influence of the carbon on mechanical properties of steel. Okay, so we talk about steel. When we talk about steel, it's up until 2% only. Up until 2% of carbon. So it changed so much in terms of microstructure. 0% of carbon, you will have 100% of ferrite. And the ferrite domination will decrease if you increase the carbon. Okay, look at this. maximum at 0.77 or around 0.8, you can see you have 100% of perlite. Okay, so if you add more carbon, you will get more cementite. Okay, cementite, again, I always mentioned earlier, it is hard. So see, because of the increment numbers of cementite, the hardness of your materials will increase. Okay, if you have 100% of perlite, you get maximum strength. Okay, but it is not so much hard. The hardness is moderate. If you increase hardness, means you will increase brittleness. So because of the brittleness, the strength is lower. Okay, the strength is lower. So if you increase strength and hardness, of course, the ductility will decrease. So this is ductile, this is hard. Okay, this is highest strength. Perlite is highest strength, ferrite is soft or ductile, cementite is hard. Okay, so now you know, if you have this portion of structure, you know how to, what is the expected mechanical properties. All right, we have about 4 more slides. Okay, fraction determination. This one is similar to the phase diagram. We have learned about this in the previous chapter. Okay, we can determine how much phases that you have at that particular temperature for that particular alloy. For example, you have 0.5% carbon. This is your alloy, and you want to analyze what is the mass fraction of each phases at this particular temperature. Okay, so of course at this point, temperature of 550. Okay, the phases present is ferrite plus cementite. Okay, cementite coming from the right side where there's a vertical line consists of 6.77% carbon. It is vertical lines mean it is intermetallic compound of cementite. Okay, so that's the reason you have cementite and ferrite. Where is perlite come from? Perlite come from this center point. Okay, all right. Again, we use the same method, which is lever rule. Okay, now this is kind of application of the phase diagram theory, right? Lever rule, we draw a line from okay, this one is considered as the most left side is a 0. Okay, the composition is C alpha. Why alpha? Because this region contain alpha. C alpha is 0, and we talk about two phases, which is ferrite and cementite. Where is cementite? Cementite also the vertical line, which is located at 6.77% carbon, 0% carbon. Okay, now we identify C cementite, C alpha composition. Okay, composition. We are not talking about determination of the composition. Now we talk about the determination of mass fraction following the lever rule. Okay, so the length between this and this is A. A, how we measure A? It is from here 0.5 to C alpha, and B, the length from here to here, how to measure it? Okay, it is distant from 0.5 and 6.77% carbon. So the fraction of ferrite, where is ferrite? It is here. Okay, so fraction of ferrite, we take the length of B, opposite side. So 6.67 or 6.77. Okay, it's, in this example, you use 6.67. Okay, 6.67 minus 0.5. This is 0.5, the alloy, and divided by 6.67 minus 0, the total length. So you got 92.5. And cementite is located here. You take the opposite side, which is the length of A. it is 0.5 minus 0 and 6.67 minus 0. So you got 7.5, or you can calculate it is equal to 100% minus 92.5%. So you got 7.5%. Okay, another example. Okay, now just now we talk about ferrite and cementite. Oops, okay. Okay. So for the same alloy, which is 0.5% carbon, we can also determine the fraction of pro-ejected ferrite and the pearlite. Okay, where is pro-ejected ferrite? If we look at the microstructure, we want to know how much pro-ejected ferrite and how much the lamellar structure is pearlite. Okay, so we want to know this. We don't want to differentiate between cementite and ferrite. We want to differentiate between pearlite and pro-ejected ferrite. To do that, so we need to identify the composition of this guy and this guy. So pearlite is here. So you need to obtain C pearlite and C alpha. So C alpha again, somewhere here, this is C alpha equal to 0. C pearlite equal to 0.77. Okay, again, similar by using the level rule. Okay, so M pro-ejected ferrite still using the C alpha. Okay, so we take the length of B. So how we got 0.27? It is 0. This one is coming from 0.77 minus 0.5. So we got 0.27. And where 0.77 come from? It is from 0.77 minus 0. It is equal to 0.77. Okay, and for the pearlite, pearlite is coming from right side, so you take the length of A. Okay, 0.5 minus 0, 0.77 minus 0, so you got this, or you also can calculate based on the 100% minus M alpha, which is equal to 100 minus 35%, and you got 65%. Okay, so any question for this? I think this one is similar to the phase diagram exercise. Okay, you can refer to lecture note of phase diagram if you don't understand this method. Okay, I think that's all for today. In some carbon alloy of ejected composition is pearlite. Okay, it's consisting of alternating layer of ferrite and cementite. The microstructure of alloy having carbon content less than the ejected, which is a hyper-ejected alloy, are composed of pro-ejected ferrite in addition to the pearlite. Okay, pearlite and pro-ejected cementite is for the hyper-ejected alloy. Okay, where you can get this, the carbon content excess of the ejected composition. Okay, meaning that larger than 0.77% carbon. Okay, mass fraction of pro-ejected phase and pearlite may be computed using level rule and a tie line that extends to the ejected composition. Okay, so this one make it consistent. It is 0.7. Sometimes for reference book, you can see it is written as 0.76, sometimes 0.7. 7, sometimes 0.8. Okay, they rounded the number. All right, I think that's all for today. Any question?